Good morning to all of you. Today we are going to talk about an algebraic structure called group. But before talking about group, we need certain terms. So let us define those terms first. Binary composition. What is a binary composition? Binary composition is a mapping which assigns order pair of elements of G to an element of G. That means it is a function from G cross G to G. For example, if G is any set and A and B are any two elements of G, then A star B is also an element of G. We say that star composition is a binary composition in G. So let us consider some examples. In the set of integers for composition addition, we see that sum of two integers is an integer. We say that addition composition is a binary composition in Z. Similarly, in the set of natural numbers, we see that the sum of two natural numbers is again a natural number. In the set of rational numbers, for the composition multiplication, we see that the product of two rational numbers is again a rational number. We say that the composition star is a binary composition. Similarly, we can see in the set of real numbers, in the set of complex numbers, that the addition composition, multiplication composition are binary compositions. So let us take another example. Let us consider the power set of S. Then we see that the composition union is a binary composition in PS, power set of S. Similarly, composition intersection is a binary composition in the power set of S. Next, but let us see what is an algebraic structure. An algebraic structure is a non-empty set together with some composition. For example, the set of natural numbers for the composition addition is an algebraic structure. The set of integers for composition addition multiplication is an example of algebraic structure. So there may be more than one composition defined in G, as we saw above in the example of the set of integers for the composition addition and multiplication. Next, we define identity element. What is an identity element? An identity element in a set G is an element of type E for which E star A is A and is same as A star E. If there exists such an element in G, we say such element E as an identity element. For example, in the set of integers for addition composition, we see that 0 plus A is same as A plus 0. That means 0 is the identity element for the composition addition. Similarly, 1 is the identity element for the composition multiplication. In the set of natural numbers for the composition addition, we do not have any element E for which we have E plus A is A and is same as A plus E. What does it mean? It means that in the set of natural numbers for the composition addition, identity element does not exist. But for the composition multiplication, we see that there exists a natural number 1 for which we have 1 star A is A and is same as A star 1. So this is about the identity element. So what we saw that the identity element in a set may or may not exist. So let us see what is an inverse of an element. What do we mean by an inverse of an element? Let A be any element of set G. We call B the inverse of A if we have B star A is E and A star B is E. And if such an element exists, then we say B is the inverse of A. And we write it as denote it like this: B is equal to A inverse. And we read it as B is inverse of A. For example, in the set of integers, for every integer A, there exists minus A. So the inverse of A is minus A. In the set of integers for multiplication, we see that there does not exist any B for which the above equality holds. For example, this B star A is equal to E is equal to A star B. For example, let us take A equal to 2, then there does not exist B in Z for which B star A is equal to E and A star B is equal to E. So this means that the identity element does not exist for the elements in Z except 1 and minus 1. So we see that inverse of an element may or may not exist in a set. So now let us define group. What is a group? What do we mean by a group? A group is an algebraic structure in which the following conditions hold. For example, first condition is the composition should be a binary composition. Associative law should hold for the composition addition. Identity element exists for the composition. Inverse of an element exists for the composition. If these four conditions hold for the composition star in G, then we say such a structure is a group. Now let us consider some examples. The set of integers for addition composition is a group. Addition is a binary composition, as we saw earlier. Associative law holds for the set of integers. 0 is the identity element for composition addition, and every element is invertible. So this structure Z plus is a group. Similarly, we see that the set of rational numbers for the composition addition, set of real numbers for the composition addition, set of complex numbers for the composition additions are example of groups. Next, consider the set of non-zero rational numbers Q0 is a group for the composition multiplication. Similarly, set of non-zero real numbers, set of non-zero complex numbers are groups for the composition multiplication. We see that Z of the set Z of integers is not a group for the composition multiplication. Why? Because every element of Z is not invertible, as we saw earlier. Set of vectors for the composition dot product is not a group. Now we consider some elementary properties of group. First property is the identity element in a group is unique. So let us say, if possible, let E and E dash be two identity elements of a group G. Then by definition, E is the identity. Then E star E prime is E prime. Also, if we take E dash as identity element, then E star E prime is E. So from this, we see that E is same as E dash. So in a group, identity element is unique. Next property is inverse of an element in a group is unique. So let us consider an element A of group G. If possible, let B and C be its two inverse. Then by definition of inverse, B star A is E, A star B is E. Similarly, C star A is E, A star C is E. Then we see that B is equal C. B is same as C. That is inverse of an element in a group is unique. Next property is cancellation law holds in group G. That means if we have in a group G A star B is equal to A star B C, then we cancel out the factor A. Similarly, if B star A is equal to C star A, then B is same as C. One thing we should note that if we have A star B is equal to C star A, then this does not mean that B is equal to C. That is, we cannot cancel out the factor A in this case. So let us take another property. A star B's inverse is B inverse star A inverse. So we see that if B inverse is A, then we have B star A is E and A star B is E. So this means that, so we have to show that inverse of A star B is this. So A star B dot B inverse star A inverse, and after computing this, applying associative law, we see that it is E, and similarly B inverse star A inverse star A star B is E. This means that A star B's inverse is B inverse star A inverse. In general, if we have A star B star C inverse, then we have it is C inverse star B inverse star A inverse. Let us take another property, that is A inverse inverse is A. Again, by definition, we know that if B inverse is A, then it means that B star A is E and A star B is E. So we have to show that A inverse is A. Right? Therefore, A star A inverse is E by definition, and A inverse star A is also E. So if A is an element of G, then A inverse is also an element of G. This means that A inverse is an element of G, and A's inverse inverse is A inverse inverse star A inverse is E, and similarly for the other side. So we see that A inverse inverse is A by cancellation law. These are some elementary properties. So next, we see that what is an abelian group? Abelian group is a group in which composition is commutative. That is, the composition follows commutative law. What is commutative law? It is A star B is equal to B star A. If a composition is commutative, then we say that the group G is an abelian group or a commutative group. For example, we can take the set of integers for addition composition is a group. We see that addition composition is commutative in a set of integers, so it is an example of an abelian group. Next, we talk about the order of a group. What do we mean by an order of a group? By an order of a group, we mean that the number of elements in the set G. For example, consider the set G consisting of elements 1, minus 1, iota, minus iota. We see that it is a group for multiplication composition. Number of distinct elements in this set G are 4. This means that order of G is 4. That is, G is a group of order 4. Consider the group of integers for addition composition. it has infinite number of elements. This means that it is an infinite group. Similarly, we see that the set of rational numbers, set of non-zero rational numbers for the composition multiplication is an example of an infinite group. Thank you.